Welcome to Walkabout the Galaxy, the cheeky astronomy podcast, where the science is universal, the opinions are personal, and the sponsors are out of this world. We are Strange, Charm, and Top the Astroquarks, also known as Josh Caldwell, Addie Dove, and Jim Cooney, coming to you from the Walkabout studios at the University of Central Florida. Show your support for Walkabout the Galaxy by following us on Facebook. Check out our website at walkaboutthegalaxy.com to find old episodes, sponsor highlights, and to purchase our snazzy Walkabout tees. Be sure to stick around at the end of the episode for the end of the episode.
That's the best part.
Yeah.
Our stumpers are cross-cultural,
Cool.
or if you prefer, intergenreal.
I don't prefer that one.
They're intergenreal.
Those are different words. Cross-cultural
those mean very
and
different things.
intergenreal.
They're more intergenreal, and you can tell me what I should have said instead of cross-cultural. Because
Okay.
they're not really cross-cultural, they're intergenreal.
Okay.
Tim,
Yes, sir.
the Mandalorian or the Manchurian?
Oh.
Do you know what either of those is?
So I just saw maybe 2 days ago for the first time a trailer or whatever for The Mandalorian, which I was unaware was a thing that was happening.
It's
I
a
guess
thing
it's
that
a
is
new
happening.
Star Wars television show.
It's a the first Star Wars live action
show. Right. And it looked like it had something to do with Boba Fett or somebody that's like
Did you
him.
say Boba Fett?
Boba.
Okay.
Boba Fett.
Sounded
Like Boba
said-
Tea.
Or it looked like somebody like that. I don't know. Maybe it wasn't actually.
It's a bounty
It's
hunter.
a bounty hunter. It's
Bounty
not
hunter.
Boba Fett. I
And
don't
apparently
think.
bounty hunters in the Star Wars universe have to wear that particular
They all have to
kind of
wear
armor.
something like that. Yeah. It looked neat, and I'm
Yeah.
not sure what the Manchurian is. There's the Manchurian Candidate,
Right.
but that's from an old thing that I haven't seen.
That's right. It's
That's a good movie.
intergenreal. It's from a
Oh.
different genre.
Oh, I see.
movie.
Okay, I get what you're doing. I'm going to go with the Mandalorian because I'm young
Oh.
and vital.
Oh.
Manchurian Candidate's a good movie, though.
It could be. I
And
have
it was
not seen
remade.
it. I have not
It
seen
was?
Yes.
Oh.
I believe Denzel Washington was in the remake.
Oh, okay.
Ooh, that
And
sounds.
I can't remember if it had the same title or a different title.
Oh, maybe it had a different title, and that's why I don't know.
It might have just been called The Manchurian, which would be awesome if that's the case, but it
Oh.
probably isn't the case.
Let's
So that'd be too
IMDb it.
awesome. Addie, Doctor Strange
Uh-huh.
or Doctor Strangelove?
Ooh, that's. I guess I feel like that's
see
easier.
what he's
I
doing
do
there.
know both of those. I'm gonna go with Doctor Strange.
Okay.
I'm actually more familiar overall with Doctor Strange.
Yeah. Have you
and-
seen Doctor Strangelove?
Yes, but I don't like. I
It
don't
made-
think I've watched it all the way through.
It made
like
me
in
very
one
happy
sitting.
when I thought of those two.
It's a very good. It's a very good combination.
Yeah.
But I think Doctor Strange.
Uh,
It's kind of cool. I don't love Benedict Cumberbatch. I'm
right.
in one of the.
How do you
I'm
feel
one of
about
the
Peter
few
Sellers,
people.
who's
I like
Doctor
him.
Strangelove?
I like him.
Yeah.
But again, I'm young, so.
Oh.
Yeah. I
To
think a
quote-
lot of
to quote
nerds
Jim.
really love the Doctor Strangelove. I did not like that.
Well, it's not
Yeah.
exactly a feel-good movie.
No, but it's
It's very Kubrickian in its
Yeah.
non-feel-goodiness.
Yeah. I generally, other than 2001: A Space Odyssey, have not been a big fan of most of.
Kubrick.
I really had a hard time, and I know that
Well,
Clockwork
it's-
Orange, for example, is supposed to be hard to watch,
Uh-huh.
but I just really did not like that, and
And so it was hard to watch.
it was hard to watch.
The
So I guess
2000
he succeeded in that, but anyway,
Right.
2001 was great.
The 2004 Manchurian Candidate,
Yes.
which was called The Manchurian Candidate,
Oh.
was Denzel Williams, Liev Schreiber, and Meryl Streep.
Denzel Williams?
Washington.
Denzel
Okay.
Washington.
All right.
Boba
I was
Fett.
wondering if I was really totally freaking out there. Doctor Strangelove, Peter Sellers played 3 roles, I think,
Oh, wow.
in that movie. He played Doctor Strangelove, and he played
The bomb.
the I can't remember the names of the other 2 characters he played, but anyway, that's a great
a-
movie. It's not a pick-me-up, but it is a great movie.
Okay.
Slim Pickens is in Doctor
Slim Pickens.
Strangelove.
Slim Pickens.
Right.
Yes.
I think we've mentioned that before because
We
he was
have.
the voice on some robot or something
That's
like
right.
that,
Yeah.
some other thing.
That
This
is correct.
Bob.
vague
It's all-
memory from a previous episode of Walkabout
That's
the
right.
Galaxy.
It's all coming together. Today we're talking about a clever way of searching through some astronomical data to find tiny black holes. Not super tiny, but smaller than the ones that are sort of jumping out of the data
You
at
can't
you.
put them in your pocket.
No. And you shouldn't put them in a corner.
You shouldn't never put a black hole
Never
in a
put a
corner.
black hole in a corner. All the different kinds of gravity waves. We'll revisit this mess about the expansion of the universe and what it means for you. But first, this episode of Walkabout the Galaxy is brought to you by The Lagrange points.
Ooh.
Mixing up genres from the blues to funktronica to disco, hip-hop, and punk rock. With the Lagrange points, you'll be dancing like the Pointer Sisters and the Bee Gees teamed up with Lady Gaga and Madonna. The 5 Lagrange points are whirling around every pair of heavenly bodies in that classic Lagrangian groove. So sync your phones to the Lagrange points for some sweet celestial rhythms to help you get around while you go around. The The Lagrange points. Where do you want to go today?
Huh.
That was an interesting choice by Lagrange points to go with that kind of advertisement.
Agreed.
Oh?
Agreed. Yeah.
The Lagrange points. They're a quintet.
They are a quintet.
They're a quintet. Mm-hmm.
Yeah. Sweet celestial groove going with the Lagrange points.
I get it. What was the line?
Where do you want to go today?
Ooh.
Hertz.
Hertz? That's a reasonable guess. That's a better guess than the actual correct answer.
Oh no.
I would say.
Where do you want to go today?
Yeah.
I don't know. It's on my credit card.
No, it's it's from the 90s.
Just tell us.
Okay, Microsoft.
Oh, okay.
I don't go any. Well, yeah, I guess.
Like
with the internet,
or something?
No, sort
was
of
like
like
pre-internet.
That was pre-internet.
beginning of having a computer you could actually take somewhere with you.
Oh, I see.
Once upon a time, computers were not something you could pick up and carry from point A to point B.
Yes. Then they put those handles on the Macs, and it
That's right.
changed everything.
It changed the world. Yeah.
Those still weren't really portable.
Space news, I-2 Borisov.
Borisov. That sounds like a...
Yes. iRobot.
E2, Brutus, or iRobot.
I-2 Borisov, which we've been updating since it was discovered late this summer, is the second interstellar comet, and we've been calling it interstellar comet, and we can now say that somewhat more confidently because water or water products have been spectroscopically identified in the stuff coming out of that object.
We have a new category in our bingo of where's water been seen.
That's right.
So water's been seen on Mars. Again.
Yes.
Probably, right?
Right.
The moon, check.
Yes.
I-2 Borisov.
Yes. Lots of icy moons, and now a comet from another star, like, shoot. I was going to say, anyway, never mind.
Yep.
A comet
exactly
from another
like that.
star, exactly like that. It has water. In comets, frequently what they do is they'll, look at the composition of these things by comparing how much of stuff A is there divided by stuff B, because they're different sizes. Depending on how far away they are from the sun, they're going to be outgassing different amounts. So it doesn't really make sense to say, I saw 50 million tons of water. That by itself doesn't mean anything. It's like how much more water was there than this other thing. Yeah. So they are comparing this, they're ratioing it to HCN, cyanide.
Okay.
It's common. Common ratio.
Yes, for comets. And of course, back in 1910, you remember...
I don't remember back in 1910.
Oh, because you're young. Excuse me. Well, some of us remember back in 1910,
None of us.
when there was discussions about measuring the composition of a certain famous comet. You remember what comet came by famously in 1910? Of course, you don't remember.
I remember it in
From personal
1986.
In 1986.
That same comet,
Halley's
Comet Halley, and they talked about HCN being detected in that comet, cyanide, which set off a mass panic.
We're all getting poisoned. That was the origin of chemtrails,
I refuse
probably.
to call it Halley's Comet, by the way. Haley's Comet.
Oh man, I can't. You and the Hadron and the Hadron and the Halleys and the Haleys, I cannot keep up.
Tomato, potato,
Right.
potato.
So I don't even know which one.
I don't
it
even
is.
know which
don't
one's
care.
right there, but I'm just saying, I refuse.
Okay.
Go ahead.
Haley's
Anyway,
Comet.
continue.
Haley's
We're all going to die
Comet.
of cyanide
I'm fine
poisoning.
saying Haley's Comet. Anyway, it set off a mass panic in 1910,
Right.
or leading up to the flyby, because the Earth actually passed through, quote unquote, passed through the tail of Haley's Comet in 1910.
Right.
So then there was this mass freak out about cyanide gas. We're going to all die from
Right.
that, which is the amounts might as well be zero. I don't even know if it was biologically dangerous, even if it weren't in zero amounts. And plus, the Earth is a big place, and the atmosphere has got lots of room for a little bit of cyanide from a little tiny pipsqueak comet.
What's the percentage of cyanide from the comet compared to the cyanide in an apple?
That's an excellent question, which maybe will be a trivia in a future
That sounds like a great
episode,
trivia
but it is
question
not,
for a future
But it is
episode.
not the trivia for this episode.
Good.
As we'll find out. I like the trivia coming up later.
I hope we do
What
too.
is it again? Oh, it's something about the universe. Anyway.
Makes sense.
Yes.
Our trivia
Hard
is
not to-
something
not to
about
be.
the
Something
universe.
about the universe.
Interesting.
Definitely takes place in the universe and has something to
Interesting.
do with the universe. So it's got all those good things. So I-2 Borisov has water just like Mars. Anyway, the ratio of the water to the HCN
Yes.
in this interstellar comet, this comet from another mother, is comparable to what we see in the ratio of comets in our own solar system. So far, this comet does not appear to distinguish itself so far with the limited measurements that we've made from the comets in our own solar system.
Boring.
So
Hopefully we find something.
Boring, but also interesting. Tells us, that
Yeah, I
other
think it
solar
might be-
systems are similar to ours. In
I
many
find it
respects.
kind of reassuring,
Right.
actually,
Mhm,
because I tend to get stressed out about our solar system being an oddball.
Right.
And I'd like our solar system not to be so odd, because I think ours is pretty cool, so it'd be cool if there are a lot of others like it.
Right.
Yeah.
That's
Right.
the way Star Trek is. Star
Right.
Trek, there are lots of other solar systems like ours.
It's a
And
very
since Star Trek
narrow-
must be real, I want all science to confirm that
But in Star Trek,
Star
there's
Trek
lots
is
of.
real.
I mean, they just go to like planets, and you don't really know what their planetary systems are like. In,
well,
in
but
a
they've
lot
got,
of the cases,
they have a lot of life forms
Earth-like
that look very
planets.
much like Southern California, with people walking around with various
amazing.
latex makeup things stuck
Uh-huh.
on their cheeks and foreheads and
Uh-huh.
noses and ears.
Uh-huh.
So that's why I think the more like the water to cyanide ratio the comets from other stars are, the more likely it is
So
that Star Trek is true.
That's true.
There
and
you
we'll
go.
be.
Solid conclusion.
We're being,
well
it
argued.
will be our existence very soon.
And I think 2061 is the year of first contact. Is that right? Can you back me up on this? Walkabout listeners will back me up on this. I believe it's April. Shoot. I
Oh
never
man, you
remember
like
whether
celebrate first contact
it's either
day.
April 3rd or April 5th, 2061. So coming up.
Coming up.
Yes.
Anytime.
And
April
they'll all be
5th.
April 5th, 2061, right?
I'm checking the year right now.
So that's all good news.
2063.
Oh, that's where the 3 is. Damn it.
Mm.
Oh, I failed
You're
twice.
kicked off the Star Trek fan club.
Man, that is a real bummer. On the
You just lost like a
I
bunch
just
of
lost
points.
a lot of gold press platinum.
Oh yeah,
Maybe I get a little bit back for saying that.
tiny bit.
A tiny bit back.
Like a yeah.
So let's talk about these tiny black holes.
Tiny
Let's-
black holes.
Let's talk about tiny black holes.
Yeah.
They sound
Yeah.
adorable.
Oh, they are.
As long as you
Also,
don't find them on your
a
face.
Still,
A
don't
good
get
song
too
name.
close to them. So most of the black holes that we know
That's what I
about
tell my dermatologist.
are either these supermassive black holes, which are millions to billions of times the mass of the sun. And
That-
we've talked lots about those, of course, on many episodes of Walk About the Galaxy. Those
And
are the
they're
ones that
like-
sit
Always
at the
talking
centers
about
of
black
galaxies.
holes.
Right. So famous active galactic nuclei.
Yeah,
things.
yeah, all kinds of fun things. And then the other kinds of black holes we talk are the black holes that form from stars that have collapsed, right? Large stars after they die blow up as supernovas, and what's left is either a neutron star or, if the star is large enough, a black hole. The thing is to find them, right? Black holes are notoriously difficult to find
Yeah.
if they're small
On
and just
account
sitting
of
there
their-
by themselves.
on
Almost
account of
like
their
they're trying to
blackness.
hide.
Yeah, their blackness. They're just sitting there. They're not emitting any light. They're not absorbing light because there's no light around them. And so how are you going to find them? Well, it's usually through their gravitational interaction with things. A lot of times they'll end up in binary star systems where they are one partner and their friend is some very large star. And as long as they're pretty close and the black hole is big enough, it's going to steal some of the... Yeah, and
That's not a
rude.
great
It's
friendship.
rude. I know.
It stretches that neighboring star.
Yeah, it's going to take that neighboring star's outer layers of hydrogen gas, and it's going to eat some of that. It's going to accrete some of that onto the black hole. And when it does that, that gas gets very, very hot as it swirls down towards the black hole, and very, very hot gas lets off X-rays.
Yeah.
Smells. Oh,
And so
X-rays.
X-rays. And so we can point our X-ray telescopes out there, and when we see very bright sources of X-rays, as part of a binary star system, we can say, hey, look, we found a black hole. And so that's how we've generally found these stellar mass black holes. And they typically are 5 or 6 or 8 or 10 times the mass of the sun, these ones that we find like that. But we suspect that smaller black holes than that exist.
Yeah, so these are black holes that are formed from a supernova explosion, a big star that's maybe 20 times the mass of the sun, burns through all its stuff, and so it has no more fuel to support its weight, and it collapses on itself, and then the remnant that's left over is too massive to be supported by any pressure that we know of. So that's what forms the black hole. And for some things, like a neutron star, that's formed when we have white dwarfs, neutron stars, black holes.
Mm-hmm.
Theoretically, we know, and observationally confirmed, that white dwarfs can't be more massive than 1.4 times the mass of the sun.
Right.
But for neutron star to black hole transition, that isn't really well known, is it?
It's not as well known. It's somewhere in the 3 solar mass range. If you're bigger than that, you're going to collapse into a black hole, but the exact location isn't known. So it'd be nice if we had a census of black holes in that small range. Unfortunately, if you're a very small black hole like that, you're less likely to be involved in one of these partnerships where you end up stealing material from your friend. But that doesn't mean that you aren't
one of those great partnerships.
That's awesome. Yeah, but that doesn't mean you won't be in a binary star system. There are still going to be plenty of those very small black holes that are part of a binary star system. The thing is, to steal material from your friend, you have to not only be pretty big, but also pretty close.
Right.
And that's going to be the exception rather than the rule. So it'd be great if we had a way...
Even though you have way more gravity, still gravity drops off, and so you have to be within a certain range to really actively be stealing this stuff.
Right. So there should be plenty of systems out there where it's a black hole and a partner star in a binary star system, but
the partner is keeping a safe distance.
So
Seems
it'd be
like
great
a good decision
if
in
we
these
could find those black holes as well. And so this new result that we were mentioning is a method of trying to find those things. And I guess the big idea was...
That has succeeded at least once.
Yeah, it succeeded. So it's basically just looking through these giant catalogs of stars that we have measured the Doppler shifts for, and looking for very large Doppler shifts, specifically very large Doppler shifts that are kind of going back and forth, shifting from redshift to blue shift and so forth. That means that something's tugging on that star. Right.
And so to do that, we have the catalog or the data can't just be how bright is the star or where is the star. It has to be measuring the spectrum, the color fingerprint, as it were, of those stars as a function of time.
Right. And so that's a non-trivial measurement to make, so it's not like we have that for every star visible in the Milky Way. It's a lot easier to just get how bright is a star at a particular time, and so we have very big catalogs of those and much smaller catalogs with these spectral measurements.
And we see that shift going back and forth. When it's going away from us, the spectrum is shifted towards the red, and when it's coming towards us, it's blue. So that oscillation, this is the same thing we use to see planets.
Yeah,
right?
So this is also how exoplanets are detected, except there it's a teeny tiny shift.
Right, so this should be a bigger shift. So it's maybe surprising to me, being fairly ignorant about how exactly this is done, that we haven't found more that way.
Yeah.
But most of the time the shifts you're going to see are not really because of a black hole. They're going to be because of another star that's just too dim to be seen.
Right.
And so it's really an exceptional circumstance where the Doppler shift is very, very large. I can calculate the mass of this unseen object. It's larger than 3 solar masses, or something like that. And so and I think that the first one that they found here was something like 3.3 solar masses. I think
plus or minus a fairly big, or minus 0.7 to plus 2 or 3. So it's somewhere between 2.5 and 6.
Right.
Is the range.
But that's just one object, right? So if we could do this for a number of objects, then we could get a better handle on where maybe that transition is. Although, having said all that, we can't really determine whether this object is a black hole or a neutron star. We just know
it's too dark to be seen otherwise.
Right.
So we just know there's something there about 3 times the mass of the sun. We can't see it, but this other big star is zipping around it.
Right. But it's cool because this is a class of black holes, this kind of massive black hole that is very difficult to find, that we predict is there, but it's really hard observationally to find. So now we're finding some.
The comparison with how we find the exoplanets is really interesting, though, because a lot of exoplanets have been found by doing this exact same thing. You look at a star, you see it's got this periodic Doppler shift, and that's this little tiny Doppler shift, because it's not going around something 3 times the mass of the sun. It's going around something like 1% of the mass.
Going around it. Yeah.
Well, but we're seeing it, right? We're still looking at the star's motion.
Yeah.
And so its motion is being perturbed by something that is not comparable to the mass of the sun, but 1% or less of the mass of the sun. Yeah. And we've seen a lot of those, a lot more than just this one black hole.
Yeah.
And that's at least partly because there probably are more planets going around
right. That's the
stars
thing is
than there are
we're
stars
pretty sure that
going
there are
around black
planets around almost every star, and though there are probably a lot of black holes in the galaxy, a lot here means maybe a few million.
Right.
Mm-hmm.
And we're talking, a few million in a galaxy with a few 100 billion stars means
that they're 1 in 100,000 or something.
Right. Rather than one for one.
1 for 1. Yeah. And the star catalog that they looked at to find this was a few 100,000 stars.
Right.
Mm-hmm.
And they found one.
So that's actually statistics of 1, but consistent with the prediction, basically, that there would be a few million of these things.
Right. So we just need to make bigger star catalogs, bigger
technique.
Doppler shift catalogs, and then we can find more of these bad boys.
Yeah. I actually want to drop the trivia on you now because it ties in a little bit with
all right.
I'm ready.
Bring it at
us. Bring it at us.
Segued into it.
Perfect.
So
that's right. Addie's looking smart today, so I feel good.
This trivia is courtesy of an article by Caleb Scharf from Columbia University in Scientific American.
Okay.
And, as is my wont, comes in several parts. We've just been talking about the galaxy, how many stars there are, all that's good stuff. And of course, the galaxy is mostly empty space.
True.
So let's try to visualize how empty it is.
Okay.
Let's imagine that we take all the stars in our galaxy, as Jim just said, it's a few 100 billion, right?
Yeah.
Let's take all those stars. We're not smushing them or anything, but we're sort of like taking them and putting them all side by side by side.
Okay. Lining them up?
In a 3-dimensional way.
Okay.
Into a big
sphere.
cube.
A cube.
I would have preferred a sphere, but the numbers I have are for a cube, but they're approximate anyway, so it doesn't really matter.
Great.
So let's imagine we take all the stars in the Milky Way galaxy, collect them together in a big box. How big would that box be? Okay?
Okay.
So it's multiple choice.
Oh, great.
Smaller than the orbit of the Earth.
Okay.
Smaller than the orbit of Neptune. Smaller than the heliosphere. When I say smaller than, I mean it fits inside that.
Yeah.
Of course, I know that if it's smaller than the heliosphere, I know that if it's smaller than the orbit of the Earth, it's also smaller than the orbit of Neptune. Okay. Orbit of Earth, orbit of Neptune, the heliosphere, the Oort cloud, or the distance to Alpha Centauri from our solar system.
Okay.
So that's the last two is essentially equivalent to like 1 light year, maybe a half a light year for the Oort cloud, and 4 light years for the distance to Alpha Centauri. So those are your 5 distances to choose from that. And
did you get that? There is a throwback to that actually. There's a reference to a parsec in the Mandalorian trailer.
Oh boy! Ooh. That's very meta.
I know.
I didn't know about that. So that's part 1 of your trivia. I'll just let you know what the part 2 will be. Is the same question for all the stars in the observable universe.
Ooh. So it's just the Milky Way
but
first.
We're starting off just with the Milky Way. You've got your choices for that. I'll give you the choices for the other one after we get to the end and we do all the answers to the trivia. There's one other bit of, it's not really space news, but news on sea level rise. Did you see this new article?
I probably saw something about it.
Well, many of you have probably seen these visualizations where you have a map and you click on it to say, like, what will the coastline look like on the Earth if the sea level goes up by 1 meter?
Yes.
Right.
Or by 2 meters or 3 meters?
And you sort of one of those like slidey things.
These sort of visualizations to show how long you have to wait before your home is beachfront property. And so somebody's gone back and said, let's take a closer look at how those numbers were actually calculated, how those maps were actually calculated. And it turns out that the elevations for the sort of where is the ground originally when they're doing those models, a lot of them were done by taking like the tops of trees rather than the ground.
What?
So they've reanalyzed that more carefully, which of course when the ground is lower than you thought it was means that the sea level is going farther up faster than you thought it was. So that's fun.
Yes, your daily dose of existential dread.
Well, just don't live in one of those cities and then you're fine.
Yeah, I don't know, fine, but...
You're not underwater.
There are some, and of course, there are a lot of places, not a laughing matter, that are already facing, as we know, famously, of course, New Orleans.
Miami.
Miami has got some issues. Jakarta in Indonesia is basically 1 meter below sea level
Wow.
starting off, and they build like crazy. There's so many people there that are sucking the groundwater out. So in addition to sea level rising, the ground is sinking.
In fact, I think the ground is, New Orleans as well.
The ground is sinking faster than the sea level is rising for some of these places at the moment. So,
and there you're only okay if, like, the only reason New Orleans still exists is we have enough money that we built all these levees and things like that to keep the seawater out of New Orleans.
Levees, interesting.
Levees?
Levees.
Dude.
Well, I love our word disagreements today.
Levees.
Vowels are complicated.
That one, I'm sure it's levees because there's a famous rock and roll song.
Yeah.
Left my Chevy.
And rock and roll singers never pronounce things wrong.
Yeah, rock and roll rules. Right. Just ask the Lagrange points.
Nice tie back.
Coming soon to a venue near you.
The Lagrange points.
Yeah.
These pictures are kind of crazy because the other thing is, right, that a lot of big cities are built on water because they're old seaports, and it's the place where you establish. It makes sense to establish cities.
Right. Yes, we live near water for good reasons.
Right.
Yeah.
So the really existentially dreadful part of this is, we look at these simulations and recognize that it's too late to stop most of this. That the experiment has been run. The carbon that we've already put in the atmosphere is not going away for a few thousand years, and so, we can hope to mitigate the problem, but we certainly can't get rid of it. So some of these sea level rises, obviously have happened already and will continue to happen for quite a long time, independent of what we do, which is kind of unfortunate. So I would not invest in Jakarta, Miami,
real estate,
Bangkok,
Key West,
these
Shanghai,
places, and it's really
all
upsetting. There are a lot of these like island countries.
Oh, really? Is
all of Vietnam?
Yeah, Cambodia.
Yikes.
Let's see. So transitioning, that leads us to a transition about gravity waves.
Ooh, exciting!
Because
not gravitational waves.
Exactly.
Gravity waves.
Which is the point. There's an analogous issue to this in the very niche field of planetary rings, which of course I will like to bring it back to. But we call the waves, the stretching of space-time, gravitational waves.
Oh, I thought you were trying to say there was some relevance to flooding and sea level change.
No,
and
just...
And I was like, that's a...
Nah.
Okay,
no.
Great. Gravity waves.
Just the Earth's climate ties in with gravity waves because there are atmospheric waves called gravity waves, and sometimes you'll see these very regular striations of clouds in the sky, and those are produced by waves of atmospheric motion in the sky. And clouds form when warm, moist air goes up, where the temperature is colder and the water condenses into droplets and get a cloud. And so if that's doing it in a wave-like motion, then you'll get a periodic structure of waves, and you can see those things propagating. And so there are some really beautiful pictures from space. And those, why are they called gravity waves? Because the force that is restoring the thing that's waving is gravity. So actually, like the waves on the surface of a pond are also gravity waves. Water gets perturbed up, gravity pulls it down, it overshoots, and the thing bounces up and down. That's a gravity wave.
Right.
So physicists call these things gravity waves all the time. There's a million, water waves, atmospheric waves, they're all gravity waves. And the gravitational wave is a completely different story.
And we've talked about those all the time.
Right. Yeah, we're not going to talk about them. We're just making sure we understand the difference.
Yes.
So this is just clarifying. This is just a public service announcement from the Astroquarks. That a gravity wave is not a gravitational wave.
And gravity waves will cause a much stronger perturbation in like measurements and stuff like that than
a
gravitational wave
for our everyday lives.
In our everyday lives.
You will never notice a gravitational wave, but you will definitely notice gravity waves in atmosphere
and atmospheric
water,
effects, and we see them on the water.
What's an example of a non-gravity wave? Sound.
Sure.
Sound waves is not a gravity wave.
Not a gravity wave.
Because gravity has not got anything to do with it.
Not horribly dissimilar. I mean, sound waves are pressure waves, density waves.
Wonderfully dissimilar, though.
They're wonderfully dissimilar, but also similar. I mean, it's, the gravity waves in the atmosphere, they overshoot, it overshoots and then gets pushed back up by pressure. So pressure is still involved in gravity waves, but it's not the driver.
Right.
I think I'm saying that right. And anyway, so yeah, but
Well, I mean,
the sound waves
so
have nothing to do with
pressure
gravity.
is-
Even in the absence of gravity, you'd have sound waves.
That's right.
Yeah, I mean,
but you wouldn't
so
have
gravity
those cool
waves or
ripples.
atmospheric waves are created when pressure, so air hits a mountain or something.
Right.
It rises.
Get
It's
pushed up.
buoyant.
Right.
And it's changes in density and pressure and stuff like that allow it to like
Right.
settle where it is,
Yeah.
and then
Gravity pulls it down.
gravity
bouncy.
tries to pull it down.
Bouncy.
And then pressure pushes it back
Pressure
up. and
pushes
so
it back
forth,
up.
Yeah.
So exciting.
It
The,
is.
uh,
They're
We talk a
super
lot about
beautiful, yeah.
balances between pressure and gravity and a lot of things in physics.
Right.
So
Yeah.
atmospheric waves, stellar centers, all of this stuff.
Yeah. The connection, the weak tangential connection to Saturn's rings is
Oh,
these
yes.
things called gravity wakes
Oh, true.
Mhm.
and gravity waves.
Gravity
So not-
wakes are when you have when gravity dies and you
And it
mourn
d-
it.
Oh, I was going to say when after gravity's taken a long sleep,
Oh, that's good
gravity
too.
wakes.
Mhm.
So yeah, so I had a real I don't know, bee in my bonnet about gravity wakes at the beginning of the Cassini mission because they're not frickin' gravity wakes. They just aren't. They
You
aren't
heard
wakes
that?
at all.
You heard
They
that,
aren't
rings
wakes.
community?
I
Josh is mad.
Anyway, I only managed to get them renamed self-gravity wakes, which is
Oh, yeah.
also terrible, but not quite as terrible as gravity wakes.
Oh, okay.
We ain't talking about those another time. Has to do with granola bars and fish sticks and things.
It does.
So, yeah, we
It
talk
does.
about granola bars
And predators
a lot
and
in our
preys.
ring- and predator and prey things.
These
Yeah,
are all very common terms in
Yeah.
the Saturn ring community.
They are. So before we hit our multi-part trivia, our third science topic was what's up with the universe, which is just a
It's a
revisit.
little topic.
We're doing lots of public service announcements today. So we're first PSA, gravity waves versus gravitational waves. Second one is just a reminder about all this business about the expansion of the universe and what's up with that.
Yeah, and we were brought to talk about this today because we saw a great article in the Washington Post about, a lot of times science articles in publications are not terribly well written. I thought this was tremendously well done and well written, so congrats to Joel Achenbach, who was a science reporter for the Washington Post. Though, I mean, so the art,
It's a great article.
It's a great article.
Except,
Well, the title is a little bit, it says, "Scientists are baffled. What's up with the universe?"
We're always baffled.
We
to be
are
fair.
always baffled. That is absolutely to be fair. But what he's talking about is something we have talked about on the thing before, but just as a reminder, it's measurements of the Hubble constant, right? So many people have heard of Edwin Hubble. The Hubble telescope is named for him.
many people have, but most people haven't.
Our Walkabout listeners
Well,
have.
our Walkabout listeners,
Yeah.
because we've talked about it. But many people have heard of the Hubble Space Telescope.
Yes.
Named after Edwin Hubble, who was a famous astronomer way back in the early 20th century. And
I'm amazed you know about it since you're so young, but whatever.
I've heard the tales.
He's a cosmologist.
But that's a measurement of how quickly, the Hubble constant is a measurement of how quickly the universe is expanding. And one of our giant problems in the field of cosmology these days is different methods for measuring the Hubble constant are yielding different numbers. And a couple decades ago, we weren't too worried about this because we had different numbers, but our error bars were large.
So
and
they overlap.
Right. And so we were all kind of happy with our general description of how the universe worked. As data gets better, our picture gets more clear. Here it's becoming less clear because
Things
we
aren't
expected as the data came in that they would all converge to the same number. They have not. They have
Right.
stayed separate numbers.
I feel like that's true a lot though when you try to scale up things, right? Because we used to have this complicated but relatively simple view of solar systems, and now as we discover more and more things, there's no solar subsystems that seem to be the same exactly. So
Yeah.
it's always whenever we find answers, we always have more questions, which is why science is fun.
Right, that is fun, right? We worried hundreds of years ago about the end of physics because we'd figured it all out, but that's certainly not the case.
It's baffling.
So yeah, we don't know. We have these multiple ways of measuring the Hubble constant. They're not giving the same answer. So the solution is it's one of two things. It's either we're wrong in one of the ways in which we're doing these measurements, which is probably the more likely thing, right? So
What?
when you're making these measurements,
Scientists?
you depend critically on all these things being carefully calibrated. One way of measuring the Hubble constant is look how far away a thing is, know how bright it is, and then figure out from that
And then see how fast it's moving.
how fast it's
and then
moving,
you
and I
go-
can compare its distance. But if I don't actually know how far away it is for some reason, because
Right.
I've not accurately
Well, Yeah, but I mean, that's the whole point of this mystery, is that that's why the error bars were big in the first place.
Right. But it
And-
could be that we're, but scientists, I mean, when we give error bars, we usually have a good justification for those error bars. But every now and again we find out we've been doing something wrong the whole time, and there's some systematic error in the thing, and
So
our
that's-
error
was that-
bars were really wrong.
Is that where you're putting your money? I don't. It's kilometers per second per megaparsec. Is
Right.
that the units for the Hubble constant?
Right. So one of
And
our measurements gives something like, if you're actually looking at how far away these type 1A supernovae are, we get something like 72 kilometers per second per megaparsec. That's how fast it's. So if a thing was 1 megaparsec away, 1 million parsecs away, it would be moving away from us
which
at
is far.
72 kilometers per second.
Which is fast.
If it was
Fast.
2 million parsecs away, a parsec being about 3 light years, if it was 2 million of those, it would be moving at 144 kilometers per second. That's one
Away from
measurement. The other measurement, based on our understanding of the cosmic microwave background, and it's very complicated to figure out how we get that, but
Yeah.
but
But this
gives
is
us
looking at the ripples,
ripples
of the temperature of the first oldest part of the universe that we can see.
right. So measurements of that tells us that the Hubble constant is something like 67 kilometers per second per megaparsec, and the error bars are smaller than that difference is like 5,
Right.
and the error bars are much smaller than that.
And back in the old days, we didn't have the cosmic microwave initially. So the first Hubble constant measurements, we didn't even have that technique.
Right.
People were measuring that other number using different sort of standard candles or
Right.
estimates for how far. And it was like, I got 65 plus or minus 10. And somebody said, I got 75 plus or minus 15. Like, it's about
it's all
70.
good. Yeah, it's about 70. That's exactly the number we used for a very long time because we didn't know. But now
And it is about 70.
It is about 70, but is it about 67 or is it about 72?
Or is it changing?
Or well, it's not that it's changed. We know that the Hubble parameter does change, but these are measurements of the Hubble constant.
Oh.
So the value of the expansion of the universe now is given by these numbers. And,
I see. Okay.
But there are many assumptions that go into our models, like for that cosmic microwave background measurement of it. A lot of things go into that. And if we're wrong about one of those things, then our measurement of the Hubble constant is wrong. So it could be some new physics is in there, like some weird thing happened in the early universe to change the nature of the cosmic microwave background, and therefore the things that we're assuming are wrong, and therefore our measurements are wrong. So it's kind of fun. I mean, it means that there's something wonky happening, some kind of new interesting physics.
Also,
something really dumb that we've done.
It points out the value of doing. You make a measurement, you're like, I got this figured out, and it sort of fits my data within these error bars. And then people go back and it's like, I want to measure that better. I want to make those error bars smaller, measure this more precisely. And a lot of times, as you said, things just work out. It's like, yep, it's still good.
Yeah.
We're still good. Everything is fine. Then sometimes you find, something weird is going on. That's where we make these discoveries. That's
right.
where all our new advancements and discoveries about the nature of things in every field of science comes from, is that sort of thing that maybe doesn't look like such a promising road to go down. It's like, well, I'm just going to do this thing that somebody else did, but more precisely and better.
Right.
And
or
lo
apply
and
the
behold,
same thing to something else and see.
Yeah.
Yep.
Yeah. Lo and behold, then you find something more interesting going
New
on.
science.
Hidden in those later decimal points. So,
all right,
yeah.
let's figure what that is.
Okay.
Let's
Get a
just
Nobel
stop
Prize.
taking data.
Yeah, that's what the joke that a lot of cosmologists are saying. We just should have stopped taking data 2 decades ago.
Right.
And we'd have been fine.
We'd have been fine.
We'd have been happy with our model. Yeah.
Okay, so have you been thinking about
I have.
how many
Oh,
stars?
shoot, I haven't been thinking about that.
Oh.
Okay, I'm going to let Addie answer first while I
Okay.
calculate.
All the stars in the Milky Way.
Uh-huh.
Put them together, and this is, so your choices are fairly different in scale. So this is kind of approximate. Take all the stars in the Milky Way galaxy, put them together, touching, quote unquote, a big cube. Is that cube the size of the Earth's orbit, Neptune's orbit, the heliosphere, which is ballpark 100 times the Earth's orbit, the Oort cloud, ballpark 10,000 times the Earth's orbit, or the distance to Alpha Centauri, which is ballpark maybe 100,000 times
How
the distance.
big is the sun compared to Earth's orbit?
Oh, I can answer that. It's 0.005 AU.
0.005 AU. Okay.
I think the radius of the sun is, I think 1 AU is 200 RS.
Okay.
Right.
Okay.
Okay.
200
ahead.
times the
You got an
radius of the
answer?
sun.
Wait,
Sure.
you were just babbling on a second ago. You said something
Oh,
about no, not
jeez.
babbling. Which one was
Mr.
1,000 times
Levy.
The
heliosphere one was the 1,000 times?
Heliosphere is about 100
about
AU.
100.
And the Oort cloud is about
10,000.
10,000.
10,000.
It's 10,000?
Oh.
The Oort cloud is this.
It's
It's
fairly
sort of
big.
there's an inner
Yeah,
Oort
I think-
cloud and an outer Oort
Yeah,
cloud.
I thought
I'm
it was
using
actually
10
farther than that, like
The Oort-
50,000 or something. But
Well, there's an
It's-
inner. I'm
it's
doing
inner and
this.
outer. There's the Taurus and the. I
If you wanna
think
say
it's the
25,000, that's fine.
heliosphere.
I think it's the Oort cloud.
It is Neptune's orbit.
I thought it might be
Wow.
smaller.
Isn't that
That's
crazy?
because that's why I was asking, right? If it's 0.005 the size of Earth's orbit, then like you can fit a
Isn't that
lot
crazy?
even within the Earth.
And
And
of
there's
course,
tiny stars and there's big stars, and most of them are tiny.
tiny. Yeah, but that's
But-
kind of mind-boggling.
I have a hard time with that because some stars are the size of Mars' orbit.
Yeah, so we're
Well, that's a good point.
we're
A handful of stars are huge and would dominate this distribution.
But Neptune's real far.
Neptune is real far.
But that's a
Yeah.
good point.
Yeah.
How did you do this calculation?
I read Caleb Scharf's article in the Scientific American, October 27th,
Okay.
2019,
Okay.
Okay.
where he
He did the
admits
calculation?
that not all stars are the same size, and there's a little bit of hand waving going on with this approximation.
All right.
Okay. Okay.
All right.
So
I
with
believe
those
it, but
sa-
I'm going to double check it. for
With
next
those same
episode.
with those same caveats, same
Okay.
question for all the stars in the observable universe. Now your choices are a box that is 1 light year,
Okay.
10 light years, 100 light years, 1,000 light years, or 100,000 light years.
Wait, so the answer to the last one was
Neptune.
Neptune's orbit. So
Which
that's
is
like
less than a
30
light
AU
year.
or something like
30
that.
AU. That's yeah.
30 AU is how many?
So there
light
are
years.
something like on the order of 1 trillion galaxies in the observable universe. So the number of stars is 1 trillion times greater than our galaxy, which means the volume would be 1 trillion times greater, which means the
Tim, you're boring us.
This is
radius
what
would be
you
10 to
sound
the
like.
3.
I know.
No,
That's why I have you guys on the show.
I don't know.
Do you get it?
I need a piece of paper.
You don't get a piece of paper. All right.
You don't get a piece of paper.
I don't get a piece of paper. Okay.
Go with your gut.
The-
10 light years.
The third one.
100 light years
Yeah.
says Addie, 10 light years says Jim, and Jim gets it 10 light years
Woohoo!
with his head math. And then finally,
That was not with him.
now take all the neutrons
Oh,
and
no.
protons in the observable universe,
Okay.
make a giant neutron star.
Okay.
Forget about neutron degeneracy pressure.
Oh man, I
Yeah.
can't forget about it.
All the neutrons and protons in the observable universe,
Yeah.
and put them together. So now, because of course
Sounds
stars
dangerous.
are much less dense than
Yes.
they could be.
Yes.
Much less dense. So if our star, if the sun were a neutron star, it'd be the size of the Earth ballpark,
Mhm.
right? So which is much smaller
The Earth ballpark.
than that. Than
Go
it
Nats.
is. So if you take everything and sort of make all the neutrons and protons in the universe
Yeah.
in a neutron star kind of state,
Yep.
how big is that? And you get choices again.
Ugh.
Neptune's orbit, Oort cloud, 10 light years, 100 light years, 1,000 light years. In the observable universe, every atomic nucleus forming thingy,
Oort
every
cloud.
proton and neutron in the observable universe,
Neptune's orbit.
it is Neptune's
Ugh.
orbit. Isn't that crazy?
It's insane, but yeah, I mean, the number of, I mean, we did this calculation, I think, in one of my classes. The number of protons and neutrons in the universe is enormous, like 10 to the 80 something.
10
Yeah.
to the 80th.
That one
Uh,
doesn't have a name.
No.
That's 1 10 to the 20th of a Google.
Yeah. It's a lot, but neutron star density is stupid. And so, yeah. That's pretty crazy
the whole
still, though.
observable universe, which is 14 billion light years,
You can
in
smoosh it down
radius,
into
yeah.
the size of
could be
Neptune.
smooched down into our solar system if you
I
crunched
mean,
all the matter.
if you crunched it all the matter, it can go into something way smaller than that. Hello,
if
Big
you,
Bang.
If you black hole it.
Yeah,
Yeah. Well, there you go.
that's true.
So,
Yeah.
The state. Yeah.
What?
Okay. Well, yeah, that's actually
The cool
an
thing is,
interesting
if
way
you
of
make it
looking
if you
at
make it really much smaller than that, it becomes a soup of quarks, which is what this show is.
a soup of quarks.
That's right.
We could call our we should call our show Quark Soup.
Quark soup. well, when
It's
we're
like
on
talk
TV,
soup,
yeah,
but
when
yeah.
we're on,
So
when,
when we go to TV,
Yeah,
our
that's right.
YouTube channel could also
When-
be called Quark Soup.
when E picks us up,
There
we'll
we
be
go,
quark
yeah.
soup.
Sweet.
Right. Well, while it may have felt like compressing the observable universe into the solar system, it was just another episode of Walkabout the Galaxy. If you liked this episode, write us a review with the wake of your motorboat and capture it on video with a drone flying overhead and share it on Facebook. Be sure to like us on Facebook to get all our updates and check out our website at walkaboutthegalaxy.com. Subscribe to our YouTube channel at Walkabout the Galaxy, where you can see Top and Charm glaring at me and our lovely Walkabout the Galaxy t-shirts. Catch up on old episodes wherever you get your podcasts. Thanks to our listeners in San Antonio, Texas.
Yay!
And around the world. Follow us on Twitter
At walk_the_galaxy.
and ask us questions anywhere using hashtag #WalkaboutTheGalaxy. Our theme music was composed by Richard Jerusik. Our production assistant and video guru is Diego Rodriguez. I'm Josh Caldwell.
I'm Addie Dove.
I'm Jim Cooney.
We're the Astroquark signing off until the next episode of Walkabout the Galaxy.
Quark Soup!